Well, good morning, good afternoon, everyone, and welcome to another exciting Exploring by the Seat of Your Pants broadcast. We've got a lot of familiar faces in the crowd. We've got a bunch of newbies too, and so if you are new to us, we are all about bringing conservation, adventure, and science into classrooms around the world. And a big thank you to you all for joining today. We've got kids from Yellowknife to Texas, so we are crossing the North American continent lengthwise. It is very exciting to have such a wide array of kids for joining us as we continue to showcase the coolest scientists and explorers on planet Earth. Now, if you joined us in October, we had a huge space month. We did, I think, 9 programs with epic NASA engineers, people working on Europa Clipper, moon missions, Mars missions, and more. It was a wild ride. And you know what? We had so much fun that we just had to keep the excitement going with our friends at the Canadian Space Agency. Now, being Canadian, this is very exciting for me. It's always cool to have NASA folks on, but the CSA does some really incredible science and research and more to explore the cosmos around us. And so today, we are going to dive in with a topic that we've only covered once in our 4,000 program history. So get ready for that. Before we get underway, very briefly as a housekeeping note, we are going to have a Kahoot today. So between our talk and Q&A, if you want to play along with a little 4-question quiz, you can pull up that game pin and do just that. It's an extra way to keep it interactive and fun. Now, I'm so pleased today to welcome in Tim Haltigin, who is joining us at the Canadian Space Agency, as I said, to talk about asteroids, these really cool bodies exploring in our solar system, and specifically the OSIRIS-REx mission, which, as I said, we've only ever covered once. So you're going to learn about a really cool cutting-edge space mission that has happened in the last few years while you guys have been in school, and we'll do a deep dive in on that. So without further ado, I'm going to zip it. Tim, welcome to the program. So nice to have you join us today, and welcome to Exploring by the Seat of Your Pants.
Thanks so much. I'm so excited to be here.
Well, we've got so many kids, and you've got so much to share with so many cool videos. So as I said, I'm going to disappear and let you do just that and take us away, man.
Oh, that sounds great. So hi, everyone. My name is Tim, and I'm a scientist at the Canadian Space Agency. So it's really cool, my job. I get to use robots to explore the entire solar system to understand how planets were made and how life started and all sorts of cool things. And so what I wanted to do today was to share with you one of the projects that we've been working on for the last 14 years, if you can believe it. We've been really, really busy, and it's been an incredible success. And so to tell you the story, really, I just want to take you back to last September. This was one of the most exciting and proud days of my life. Right now, it doesn't look like a whole lot. It looks like a little black capsule, sitting on the floor of the desert in Utah in the United States. But what this capsule represented was, over a decade of work by thousands of people. And inside of it was some of the most precious cargo in the history of space exploration. Inside of this container was a small piece of an asteroid. And so, you might be thinking, well, okay, I don't know a lot about asteroids. What is an asteroid anyway? So if you ask our friend Google, if you type in just asteroid, I did this morning, this is what pops up, pictures of rocks flying through space and sometimes crashing into planets and, blowing up dinosaurs and things like that. And so I think the stereotype of an asteroid is just, it's this thing that flies really fast through space and it kind of blows things up sometimes, so why would you ever bother trying to collect a piece of an asteroid? I mean, why would you spend so many years and have so many people working on a project to go get a piece of one of these things? Well, so really, when you think about an asteroid, instead of thinking about it as some, destructive thing flying through space, what I want you to think about is that asteroids actually are the key to unlocking some of the most interesting questions in the history of the solar system, like where do planets come from and how did life start? And so by studying asteroids, really what we're doing is we're studying a history of the solar system. So if you wind the clock back, instead of to last September, if you wind it back even further, and this time we're going back 4.5 billion years, with a B, billion years. At the beginning, when our sun was just forming, at the very beginning of the solar system, there weren't planets. There was just this giant swirling disk of dust and gas, and it was just going round and around and around. And what happened is that tiny bits of this dust and other tiny bits of this dust would pop into each other and sort of crash into each other and stick together. And then those bits grew and they knocked into bigger bits, and slowly and slowly and slowly more things started colliding, and eventually you had sort of these bigger and bigger and bigger bodies forming. And as these bodies continued to collide and grow, the bigger they got, the more they attracted more material, and the more collisions there were, and there was all kinds of stuff happening with all this material coming all together. And really what this was, at the end, that's how planets are formed. It was just tiny bits of dust that started in the first place that bonked together and stuck together and grew and grew and grew until we ended with the planets that we see in our solar system today. But what's neat is that not all of the material that from the beginning of the solar system made it into planets. Some of it was sort of leftovers, you know, kind of like when you're cooking in the kitchen and you're prepping dinner. A lot of the stuff gets in the pan, but sometimes there's a bit of a mess on your counter. Well, really, that's those leftover bits, you know, in the cosmic kitchen. That's what an asteroid is. It's a small piece of rock that grew a little bit in size, but didn't make it all the way into a planet. And so now we know of about 500,000 asteroids in the solar system. And so they're all over the place. It's really, really, they're amazing, amazing bodies. And so, well, okay, so the question is, why is this relevant? You know, so why do we want to know about asteroids and what they're made of and stuff? So one of the most fundamental questions that we're trying to answer in space exploration is, how do planets form in the first place, and how do they evolve? And so the way I like to think about it is, imagine the Earth as a chocolate chip cookie, right? So planets, like cookies, when you make a cookie, you have to mix a lot of ingredients together, and you stir them, and you make little forms out of them, and you bake them. And when you bake them and heat them up, some of the materials change and mix in different ways. You take it out of the oven and they cool, and sometimes they dry out and they crumble and little bits break off and stuff like that. And that's sort of what happens with planets. With planets, what happens is all those pieces that came together over time, they heated up really, really, really hot. There was a lot of changes to the chemistry of what these things were made of, to the shape. We grew an atmosphere. You know, we got oceans, things dried out and cooled down a lot. And so we really don't resemble what it was like in the beginning. So, you know, just like with cookies, we know how they're made. We sort of understand how things mix together. With planets, we understand sort of how they mix together and things like that, and the general process. But really, if you're going to an asteroid, ultimately what you're doing, it's like going back into the cosmic cookie dough and getting, you know, a piece of flour and a chocolate chip and a grain of sugar. You're going back and getting the raw materials of what planets were made of in the first place, before all those ingredients mixed up and heated up and then cooled and dried. So really, if you go back and get a piece of an asteroid like we tried to do on the OSIRIS-REx mission, this is the equivalent of going back in time by 4 billion years and getting some of these raw materials from the very, very beginning of the solar system that haven't changed over the last 4 billion years. And so getting a piece is like going into a cosmic time capsule and seeing what the environment was like and what the materials were like at the very, very beginning of the solar system. So how did we do this? Well, it was an amazing, amazing mission. So this was September the 8th of 2016, under a perfectly cloudless sky at the Kennedy Space Center in Florida, in Cape Canaveral. And our rocket, on top of our rocket was our little spacecraft about the size of an SUV, and it took off perfectly on time, an absolutely flawless launch, and we were off, and a lot of people were celebrating a lot. But it was a bit of a time before we actually reached the asteroid that we were chasing. So after the launch, what we did is we actually had to fly all the way around the sun. So it took us about a year to fly around the sun, and we sort of were catching up to the asteroid, but not quite. So what happened is we actually made it back to Earth, and we flew under the Earth, and the gravity from the Earth actually changed the direction that the spacecraft was flying. And so it tilted it at the right angle so that we could go and actually find our asteroid. So it took us about 2 years and the spacecraft had to fly for about 2 billion kilometers. But finally, in December of 2018, we finally made it to our asteroid Bennu. And when we opened our eyes and turned on our cameras, this is what we saw. So it was a very, very rocky asteroid. You can see thousands and thousands of boulders all throughout the surface, some giant rocks growing off of the side. And this was a huge surprise to us, because we were expecting a very, very smooth surface and one that would be relatively easy to use the spacecraft to go and get a sample of and to come home. But instead what we saw was this really, really scary rock with lots and lots of hazards. And so our whole science team and our whole engineering team had to figure out, well, what were we going to do? How were we going to study this asteroid? And how were we going to find a place on it that was safe enough to put the spacecraft down and get a piece of it and to come back to Earth? So just for context, if you were to take asteroid Bennu and plonk it down in the middle of downtown Toronto, this is what it would look like. So it is just about the height of the CN Tower. So any of you who've ever been to Toronto, it's just slightly bigger than the CN Tower. If anyone's been to New York for our American friends, it's about 1/3 higher than the Empire State Building. So this is a body that's about 500 meters across. It's flying through space at over 100,000 kilometers an hour. It's only reflecting about 4% of the light that hits it. So it's almost like this black, lump of charcoal, it looks like. It's spinning. So it spins once every 4 hours. And it takes about 1.2 Earth years to get all the way around the sun. So basically, here we were with this 500-meter lump of charcoal with boulders all over it, spinning once every 4 hours and flying through space at 100,000 kilometers an hour. And we had to figure out how to go and get a piece of it to bring it home. So it was a huge challenge. But thankfully, we had an absolutely outstanding spacecraft. So this is an image. This is an animation of what our spacecraft looked like. So this is the deck. We also like to call this the family portrait with all of the instruments on board. And so we had different types of cameras that worked from different distances away and had different resolutions to help us understand what the asteroid looked like. We had tools called spectrometers, and these are really, really neat instruments that measure the type of light that bounces off of the surface. And by measuring different types of light that come off, you can actually tell what the asteroid is made of, which was pretty cool. And then in the top left here, we have an instrument called OLA, or the OSIRIS-REx laser altimeter. Now, this was the instrument that Canada had provided to the mission. So this was our contribution to the spacecraft, and an instrument that I've worked an awfully long time on. So here's a picture of the actual hardware that we use. So the instrument comes in 2 boxes, and they're roughly the size of sort of a toaster oven. So on the left side is a box with that has all of our electronics and our power. So it deals with all of the data, it turns the instrument on and off, and it collects the data. So that box was inside the belly of the spacecraft to keep it nice and safe and warm so that all the electronics worked. On the outside was the box on the right. And so you see that window on top of it. That window was very, very important to us because the way this instrument works is that we actually had to fire lasers out at the asteroid and measure the light that came back. And so the way it works is sort of like, maybe you've seen a laser rangefinder at a hardware store. Maybe you have one at home where you can sort of point it at a wall and say, okay, the wall is 3.4 meters away. Well, it's a very, very similar process here, where with the spacecraft, with our instrument, what we would do is we would send a pulse of light out, and it would fly and hit the surface of the asteroid and come back. Some of the energy from that light would come back and be measured by our instrument. And so if you measure very, very accurately the time it takes for that light to go out and come back, essentially what you're doing is you're measuring a distance away from the spacecraft. And so what you can do is, if you do that, 10 times at different locations, or 100 times at different locations, or even 1,000 or 1,000,000 times at different locations, eventually what you start doing is building up a three-dimensional shape because it's different distances to different points on the surface of the asteroid. So imagine doing that millions and millions of times. And for us, imagine we did it over or almost 3 billion individual times. So we shot the lasers from our instrument nearly 3 billion times to measure different points on the surface of the asteroid. And this has become the most detailed three-dimensional map of any body that's ever been explored anywhere in space. So it was a super cool instrument, and the data we got back from it was just amazing. So this is what it looks like. This is what happens when you put 3 billion laser measurements together to put together a three-dimensional shape of this asteroid. And so this image that you're seeing right now was not taken by a camera. This is purely done by shooting lasers at it and measuring the time that it takes to get back from all of those different locations. And what's really neat here is that this asteroid, like we said, is 500 meters across. So it's like the size of the CN Tower, but we now understand its shape all the way down to 1 point every about 4 or 5 centimeters. And so it's just incredible the amount of data that we were able to collect and put together to represent what this asteroid looked like and the shape of it was. And part of the reason that was so important was to make sure that we could then look at all the data and we could put that data onto our computer and find where are some of the smoothest locations, where they're the least boulders, where is there a place on the surface of this asteroid that we can actually take the spacecraft to collect the sample. And so after studying the entire globe of the asteroid, originally we started with 16 candidate sites and we narrowed it down to 8. And finally, there were 4 finalists. And we went in and measured very, very, very detailed measurements at those 4 locations to make sure that we were going to pick the right one. And so it ends up that as a science team and as an engineering team, we sort of got together and figured out what would be the safest, what's the most reliable place to go and do this. We selected the site that was close to the North Pole. So it was the northernmost, the top site that you see in this image here, that ended up being the best decision for all of us. And so what happened after we decided where we were going to go is an arm about 10 feet long extended from the belly of the spacecraft. So think about the height of a basketball net. And at the end of this arm was a circular piece of technology called the touch and go mechanism, or TAG. And slowly we descended down to the surface of the asteroid with this arm extended. And what we were going to do is make contact with it and puff out some gas to sort of stir up gravel and dust and things like that. And so this is real imagery of what it looked like at the moment when we collected the sample from the asteroid. So there it was coming down to the surface. And finally, we made contact. We puffed up gas and dust. And what happened is that some of that dust and small bits of rock made it into that tag mechanism, that the sample collection at the end of the arm. And it was great because we were happy, we were successful, we made it. And what happened then afterwards is, here's an animation. So the spacecraft slowly backed away to a safe location. The arm folded back up, and we had the opening of the sample return, the Earth return capsule open. We put in the head of the tag and locked it up. And so you might recognize that circular container on top of the spacecraft from the very first slide of this presentation. That's what came home to Earth. And so here's an image of the lid actually closing. And that was the moment that we knew that we had safely collected a piece of an asteroid and it was ready to come home. And so it's amazing to think that, we had thousands of people working on it for over a decade, and it all came down to contacting the surface of the asteroid for less than 30 seconds. We flew for 2 billion kilometers. We studied it for 2 years, and so there we were in 2020 with a sample safely inside of the Earth return capsule. So we were ecstatic. But the spacecraft was in the wrong place to come home to Earth, and so we actually had to hang out for a while until it was the right time to depart the asteroid. So we ended in space, and then we ended up having to fly home for about 2 years or so. So another 2 billion kilometers. And the spacecraft finally made it back to Earth in September of last year and released. So the main spacecraft stayed in space, but it released this Earth return capsule that was sort of about this big, and it targeted the Utah desert where we knew it was going to land safely with its parachutes. And so this is the last image we have of the Earth return capsule leaving the spacecraft on its way to Earth very early in the morning of September the 24th of last year. And thankfully, a few hours later, there it was sitting safely on the surface of the desert. With the parachute off in the background that allowed it to land safely. And we did it. And there was a huge sigh of relief, and the whole team exploded with excitement because this is something that, was a drawing on a napkin in 2009. And here we were in 2023, having safely returned the sample back to Earth. So it was a spectacular moment, and we were just so proud. And inside of it is some of the most spectacular, exciting material that you can ever imagine. The material inside that we brought home has not changed for the last 4 billion years. And so the sample was taken from Utah. We wrapped it up very, very safely. And the team took it back to the Johnson Space Center in Houston, where there's a very, very special room that they put it in, and they opened the capsule, and we finally got to see what was inside. And so we have materials that range everywhere from tiny bits of dust to the largest piece that we have is about maybe 2 or 3 centimeters across. And so the total mass that came back was 121 grams. Now, this might not sound like a whole lot. That's sort of a few teaspoons of material overall, or a few tablespoons. But what's really, really exciting here is that this is the largest mass of anything that's been brought back from anywhere in the solar system since the astronauts were standing on the surface of the moon in close to 50 years ago. And so it was a tremendous success. And studying even individual grains of this material, micrograms of this material, will allow scientists to unravel mysteries for decades. And so having over 100 grams, our goal was to bring back 60. And we ended up bringing back over 120. So we more than doubled what we thought would be successful. So it was incredibly, incredibly successful. And what's really neat too is that because of the collaboration that Canada had with the United States on this mission, is that Canada is actually going to receive a portion of that sample coming back. So we get 4% of the material that was brought back to Earth. And this is one of the reasons I'm so excited and so proud to have worked on this mission, because we did a lot of great science while we were at the asteroid, and we took a lot of amazing measurements, and we wrote hundreds of papers about what we've learned. But now we actually get to study the samples themselves and to understand, is this where the building blocks of life came from? Is this how water came to the early Earth? We get to answer fundamental questions about how our planet formed and how it's changed over time. And the thing about sample return missions is that this is sort of like, I like to think of them as the gift that keeps on giving. So this is a picture of Harrison Schmitt, the last geologist that was on the surface of the moon close to 50 years ago, or over 50 years ago. And we are still making brand new discoveries today on those rocks that they brought back from the Apollo missions, because we have tools that just flat out didn't exist 50 years ago. Like, think about the change in just your telephone over the last 2 years. Now imagine, project that 50 years in the future. Imagine the types of technologies that are going to exist. What's the same with science instruments? We have better and better equipment to study things that we never were able to study before. And what's even cooler is that we know how to ask questions that we didn't know how to ask before, because we've learned so much over these 50 years in studying the moon. We get to ask better and better questions as time goes on. And so for me, thinking about, what we're going to learn from the OSIRIS-REx samples, it's not just a question of, what are we going to learn, now in 2024. But what are we going to learn in 2034 or 2044 or 2084? I mean, it's incredible. We're paving the way for generations and generations of science to happen. And so that's why it's so important that you're ready to study them. I mean, it was our job to go get it, but it's very much your job to be ready to study it, because these are things that we're going to be able to make these samples available to scientists for years and years and years and years. And so there's people in high school and in grade school and in kindergarten and people that haven't even been born yet that are going to be making some of the most amazing discoveries on these samples. And so we've got them, we brought them home, they're safe, and we're making them available for decades and decades to come. So we're super, super excited. And what's even cooler is, only a portion of the spacecraft came back and landed on Earth. We still have a very, very healthy spacecraft out in space right now. So after it dropped off the Earth return capsule, the spacecraft actually kept flying through space. And because it's in such good health, and because we still have a lot of fuel left, we've actually decided that we're going to take it to another asteroid to study more things about different types of asteroids and what happens when they fly really close to planets. And so keep an eye out in 2029, which I know sounds like a long time away, but it's really not. There's going to be an asteroid called Apophis that flies very, very close to the Earth. And we're going to use our spacecraft with the cameras and the spectrometers and our OLA instrument to understand what it looks like, what it's made of, and what its shape is, to really unravel mysteries of different types of asteroids. And so the adventure is continuing, and we've still got an awful lot of work to do. So with that, I will say thank you so much for listening, for participating, for being a part of this. There are few things that I love more than science. And I'm just so grateful that as educators and as classrooms and as students that you're able to participate in activities like this, because the whole point of being a scientist is to ask cool questions. And what I hope is that this presentation and other ones that you see allow you to ask some of those questions. So thanks so much.
Tim, thank you so much, man. That presentation had everything. We've got like cool spacecraft in a desert. We've got 2 billion miles of flying. We've got space lasers. We've got cookie references for planetary formation. That was awesome. Thank you so much. What we're going to do now is dive into a little Kahoot together. And then after that, we're going to go to all our classes for questions live, YouTube, all of you. Get those questions ready if you're on YouTube. And so, Tim, I don't know if you're familiar with Kahoot, but we're going to have our 4 questions here. The faster the kids answer, the more points they get. And what they win is our everlasting respect. So good luck to everybody. And Tim, if you want to help us out with any of the answers with like a few seconds to spare, give us little hints. That might be very welcome. We're going to go to our Weisbrot Cochrane crew first when we do our Q&A, but get on in with our game pin and find out who was paying extra close attention today. So much fun. I want to stress, too, all our classes, Canadian Space Agency has so many amazing resources, and there's tons on the OSIRIS-REx mission. So if you're keen to follow up this broadcast with some more learning, I will make sure you all get that in an email when we are done. But for now, let's dive in together. Avoca West, you're going to be third. Mr. Hugh Miller, you guys are with us. SOF crew, you guys can share. And then our YouTubers, we look forward to your questions as well. But our first question in our Kahoot is, it's off to study asteroid what? What's the name of the asteroid? Who is paying attention? OSIRIS-REx, is that the name of the asteroid? Is it Bennu? Is it BZDDGGH124, very technical term? Or is it Apophis, which we also might have learned about at the end there? This is a bit of a tricky one. Tim, what do we think? I don't know. You mentioned at the beginning, we had a few notes. Oh, wow. You guys are like really on the ball. Yes, Bennu is our correct answer. Way to go. I'm surprised as many of you got that right. Way to go. Shining Cheetah has our lead. And if you just want to yell these out in your class, that's totally fine as well. Question 2, asteroids are made of what? We picked up these samples. You saw a bit of it at the end. Is it ice? Is it rock and metal? Is it star stuff, the same stuff that makes up our sun? Or is it we have no idea? We have no conception of asteroids. There's a little nuance here, but by and large, when we think about objects floating around in our solar system, we think about asteroids as being made of rock and metal, which most of you got. Very, very good. Comets are ice, by and large, or ice and rock together. And so that's one of the big differences between the two. But they know, Tim. They're on the ball, man. They were.
Oh, they've got it.
Shining Cheetah barely with a lead over Creative Iguana. Question 3. OSIRIS-REx did what with its asteroid sample? It left it floating around. It dropped it off on Earth. It lost it. Oops. Or there was no sample. I mean, we saw this. I must say, like, you know, professional detachment aside, seeing that craft in the desert is so cool. Like, it's so awesome. And to be involved in the mission would be beyond amazing. So I'm so happy you had that chance and it all worked out so well. Yes, dropped it off on Earth. That's what made it so cool. So Shining Cheetah keeps our lead by like 8. This is like down to the wire. No idea what's going to happen with our final question. Okay, this is not in the talk. I just wanted to throw this in because I think it's an important note. Flying through the solar system looks like this, where you're like the Millennium Falcon, dodging asteroids everywhere. Is that true or is it false? What do we think? I'm really interested in the answer to this. I like to throw this in asteroid talks because I certainly had a different view of this when I was your age. Ooh, okay. So yes. So Tim, there are millions of asteroids out there, but space is huge. So it's not, you're not worried about hitting one just generally. The issue is actually finding one out there to begin with and having the math to get it where you need to go, correct?
That's right. So certainly, yeah, we know we have about 500,000 in a catalog that we know very, very well, and there's more out there that that we haven't found yet. And so there's an amazing amount of asteroids out there. But yeah, like you said, space is gigantic. And so there's no stress as you're flying to one that you might accidentally bonk into another one. Sometimes there's problems with, dust particles that we can't track and things like that. But running into a whole other asteroid, I think is not going to be an issue at all. So as much as I would love to fly the Millennium Falcon myself through the asteroid belt, no, it's not a stress. We had a lot of room. But actually, it's a good question because, it sort of makes you think, well, why did we choose this one out of all of the 500,000 that we had at the beginning, right? And so it's really neat. You'd think that we had a lot to choose from, but really, once you start narrowing it down, there were fewer and fewer that made sense for this particular mission. And so if you start with that 500,000 that we know of, there's only a certain number of those that had the correct orbit that we could actually get a spacecraft all the way to in a reasonable amount of time. So that narrowed it down a little bit. And to narrow it down even further, of those, there were only fewer that we were able to get a spacecraft to and back to Earth in a reasonable amount of time, because this is a sample return mission after all. And so we had to get there and home. Of those, there were only a certain proportion that were the right size. So the way it works with asteroids typically is that the smaller they are, the faster they spin. And the faster they spin, the harder it is to try to get a spacecraft down and contact it safely. And so we were looking for asteroids that were at least 200 meters across. So that narrowed it down even further. Of that, there were an even fewer amount that were made of the types of material that we were the most interested in. So there's different types of asteroids out there, like we had in the Kahoot. There's some that are primarily rock. There's some that are more metallic. And based on information that we can collect from Earth, we have a pretty good idea of sort of the different categories of asteroids that exist. And so the type of category that we were the most excited about, things with lots of carbon on it, there were even fewer of those. And finally, that narrowed it down to like 5. And finally we had, and it ends up that OSIRIS-REx Bennu is one of the asteroids that flies very, very close to Earth every 7 years or so. And so one of the things we wanted to do was understand its orbit very, very, very well to make better predictions about where it's going to be in space over time. And so even, starting with 500,000 to begin with, we narrowed it down to that one that was the target of the mission.
Very cool. Thank you, Tim. What a cool answer to lead us off in our Q&A. We are going to head to our Cochrane crew now, grade 3s. Elizabeth Barrett, if you guys want to unmute your mic, come on in and take us away with our first question. Hey, guys. Hello.
Hello. We have Alex with a question.
Hey, Alex.
Approximately how many asteroids are in the asteroid belt?
So we know of, like I said, about 500,000 or so that we have in a catalog. So we've got some pretty good information about a lot of those. But that's not all of them. There are some probably that we haven't been able to detect yet. So we're constantly on the lookout. There's teams of people throughout the world that it's their job actually to search for asteroids. And there's new missions that are going out that are actually able to see asteroids that we haven't been able to see before. So we're constantly trying to add to this catalog, because the more we know about, the better off we're going to be.
Yeah, great question to lead us off. And I think for our kids' perspective too, imagine going out at night and looking for like a little sparrow flying way away as far as you can see, and how difficult that is. Well, it's way easier to see a little sparrow at night far away than it is to see an asteroid in the asteroid belt. This is a huge, huge area. Some of these rocks are very tiny and they're really far away. So it's like the most cutting edge science to be able to find that. I'm actually quite amazed that we have 500,000 that are in a catalog, which would be just like the biggest catalog ever. So many pages to flip through. So a cool question to kick us off. Thanks, Alex. Avoca West, grade 3s, Illinois, come on in and take us away, guys.
Come on up. Number one, we have a bunch. So whenever you have an opening,
We're coming back.
Did the samples that you have did you find them radioactive?
Were they? Oh boy, that's an exciting question, isn't it? So were the samples radioactive? Well, the short answer is no, which is good, because the types of elements that are radioactive weren't found. They didn't make up this asteroid. So the samples that we have back on Earth are very, very safe to work with. The special rooms that we have to work with them and to store them, that's mostly to keep it, instead of keeping the Earth safe from the rocks, it's more to keep the rocks safe from Earth. So it's one of the cleanest rooms that you can ever imagine. We've got very, very special containers to make sure that there's no contamination that can get in and change the rocks themselves. And so we're more worried about protecting the rocks from things that the Earth might do to it in terms of water or bacteria or temperature changes than we are worried about what the rocks could potentially do to the Earth.
Yeah, what a cool question, though. We've never had that in one of our space mission things ever. So thank you very much for that. Mr. Hugh Miller's class, Waterloo, you guys could become future space engineers. You're in one of the hubs for this in the world. So grade 7-8s, come on in and take us away, guys. Hey.
Oh, there you are, everybody.
Hey,
Can
guys.
you hear us okay?
Yeah, you're perfect, man.
Okay. Douglas in the front row there at the end had a question. He's hiding now. His question was, have there ever been like similar missions where there's been like a craft sent out that's like crashed into an asteroid, or also kind of combined with that, are there ever any like crafts or unidentified things that are picked up on the trajectory while it's traveling to or from an asteroid that are like kind of reported to like NASA or to the science people that are observing it?
Yeah, cool question.
Great. So if I understand it correctly, have there ever been any sort of failures in terms of the spacecraft that are going out to asteroids? So the answer is no. We've had some very, very successful missions. This is the first time that NASA was doing an asteroid sample return mission, and the first time that Canada has been involved in one of these missions. But Japan has successfully returned samples from asteroids twice, the Hayabusa and Hayabusa 2 missions. And what's neat is that they studied different types of asteroids and brought back material from different asteroids. And so one of the great things we can do in collaborating with our friends from Japan is compare the materials that we found on Bennu with the materials that they found on the asteroids that they collected from. And so by international teams and countries working together, what we're able to do is learn more and more about the solar system as a whole. Now, there is a mission where a spacecraft crashed into an asteroid, but that was very much on purpose. So this was the DART mission. And so this was a mission to test some technologies to say, what would happen if an asteroid was on a collision course with the Earth? If we could send a spacecraft out and smash it into an asteroid, would we be able to change the direction enough so that it would miss? So it was, I think, it was last year, the year before, it was very recently, the DART mission actually took its spacecraft and flew into an asteroid. Now, this was an asteroid that posed no threat whatsoever. It was really far away. It wasn't close to the Earth, but it was just a demonstration to say, if we smash a spacecraft into an asteroid, we can change the direction that it's flying. And it was a massive, massive success. So what was really neat is what the teams demonstrated is that you can change the orbit of an asteroid if you smash something into it really, really hard. And so this is one of the ways that the world is working together to say, what is an option in case an asteroid was coming towards the Earth. Now, the good news is, of these 500,000 asteroids, we know the orbits really well, and there's no risk posed of actually anything sort of making contact with us that's of any great size. But the good news is that there are teams that are preparing for future. Yeah.
Yeah. I love Project Dart. We have done a program on it in the past, and it's so cool. Everyone should look it up. It's so neat, and I love that we got that question. So thanks, Mr. Huemiller's class. We've got one from our Yellowknife crew. Welcome in, Miss Sampson's class. They're on YouTube, and they wanted to know if you were in space as part of this mission. Have you ever been to space? Can you tell us a little bit about how people involved in space missions do or do not go to space? Because I think it's different than a lot of people think.
Sure. No. So I have never been to space. This mission was entirely robotic, and so it didn't have any people on the spacecraft at all. It was just a machine, a vehicle that we built with all the instruments on board. And the way it worked is that we controlled it from the Earth. So what would happen is, as the spacecraft flew out, we had to beam commands to it. So we had a big antenna, and we would write some computer code and send it through this antenna out to the spacecraft. And the spacecraft would receive those commands, and the computers inside would execute what we asked it to do. But what was neat is that the further away that the spacecraft got, the longer it took for that signal to get there. And so it wasn't like we were sitting there with a joystick doing this in real time. We would have to beam it. We only had one opportunity per day to send a day's worth of commands, and it would go and do its thing, and then it would send the information back, the data that it collected, and we would use that information to make decisions about what we were going to do next. And so that's why it was even more spectacular. So as incredible as it is to think that this is a spacecraft that touched down on an asteroid that was going 100,000 kilometers an hour and spinning once every 4 hours, it did it by itself. It had to make its own decisions. So when we found out that it was so rocky, we actually had to change the way that the spacecraft was going to operate to go down. And so what we did is we gave it a map, a very detailed map of the surface of the asteroid. And as the spacecraft was flying down, it was taking pictures, and it would compare those pictures that it took to the map that it had in its memory to say, am I in the right place or not? And as it got closer and closer and closer, it was constantly saying, am I still doing okay? Am I still doing okay? Am I still doing okay? And that's how it made it down safely. So we weren't able to command it real time. It had to just take our commands and sort of make its own decisions. So it's really remarkable. Now, in terms of people going to space, it's another thing entirely. So the last time that Canada was hiring astronauts was in 2016, 2017. And I was lucky, actually. I did make it through several rounds of the selection process. It was one of my dreams as a kid, was to go into space. So ultimately, Canada selected Josh Kuttrick and Jenny Sidey-Gibbons as their 2 new astronauts, and they made a fantastic decision. They're representing Canada beautifully. And so they're training in Houston right now for some upcoming missions, and we're just super, super proud of them.
Yeah. Thank you so much for all that, Tim. And they are great people. We've had Josh on before, and we've had Jenny on before. We've had Jeremy Hansen. So we've had 3 of the 4 active Canadian astronauts.
Nice.
Very fun. And a whole bevy of amazing teams, because thousands and thousands of people are behind the science, engineering, and more decisions that happen at the Canadian Space Agency, at NASA, at these space agencies that are sort of exploring the bounds of our solar system and beyond. So I love when we get that question. Thanks,
For sure.
Tim. Now, time flies when we're having fun, so we are at the technical end of the broadcast, but I want to do a rapid fire round if you're good with it. To sneak in a
Let's
few
go.
questions. Cool.
Yeah.
Okay. So we're going to keep these as punchy as we can. Classes, you can always email us extra questions after, and we'll try and find the answers on absolutely everything. So please feel free. Cochrane crew, we're going to come to you first. Come on up. Hey, guys. Grade 3s, welcome back. Hello. So many of you. I love all the hands up. I know. We could take questions all live long day. Hi.
How many missions have you went on?
Ooh.
Have you
How
been
many
part
missions
of? Yeah.
have I worked on? Oh boy. So I have worked on a few. This is the one that I've worked by far the longest and hardest on. I helped the Mars Science Laboratory mission a little bit when it was landing, to try to figure out where it was going to land. And also I'm involved in planning for a sample return from Mars. So I'm helping out NASA and ESA, the European Space Agency, to figure out how we're going to bring rocks back from Mars.
One of the coolest missions out there. We've covered that a bunch, and I really, again, encourage our classes to look that up. I'll share some cool space resources when we're done, but great question. Thank you for that. Avoca West, grade 3s, come on back in, and Mr. Huemiller will wrap up with you in a sec. Hey, guys.
What's the biggest asteroid you guys have seen?
Ooh.
Holy cow, that's a great question. So it depends. So the asteroids, as they get bigger and bigger, we sort of call them small minor planets, actually. And so there's I can't tell you the exact size of it. Maybe, Jesse, what I can do is I can get back to you with the name and the size of the biggest one.
Please. Yeah. Are we talking about Ceres and Eris?
Yeah.
Or yeah. So there's two that are sort of, I'm not wrong. There's two that are like iconically big, and then there's others that are like approaching that. But there's two that are they're the size of moons. Like they're as big as moons in our solar system, and they're just in the asteroid belt, which is super neat. So I'll put the names for them so you guys can check them out. And Eris, with weird capitalizations and spacing, but I'll get it up as soon as I can. It wants to work. Thank you. There we are, Ceres and Eris. So check these out. They're really cool. They're in the same category as Pluto now. Poor Pluto. Mr. Humiller's class, we're going to come to you guys to wrap us up, and then we'll say a big thank you and farewell from everyone. Thanks for this rapid fire round, Tim. This is great. 7/8, come on back.
Everybody wave. Hello.
Hey. Hello. Do you have any other questions for us before we go?
We have one that could be a rapid fire.
Go for it.
One student, Aiden, who's just sitting over there, possible future astronaut, hiding behind there. Wondered if could you go in the reverse direction of, instead of following the trajectory of the asteroid, could you go in reverse and get there faster, or would that work to do that?
Interesting.
In theory.
Trust me, we got there as fast as we could. There were a lot of awful smart people figuring out the best trajectory. We wanted to take the least amount of time and use the least amount of fuel and have the least amount of risk along the way. So it was as fast as we could get there and home.
Yeah, it's, there's so much extra fuel and work and things that go into getting spacecraft to where they need to go that it's like the best math people on planet Earth. Imagine trying to like throw a dart and hit like a bullseye from across the United States or Canada. And that's not even remotely getting close to how difficult it is to get a spacecraft to a little tiny body like Bennu in the immensity of the solar system. So I love when we get this question. Thank you so much for that, guys. Tim, this has been great. Thank you for your passion, your expertise, a beautiful presentation. You are welcome back anytime. And as we do to wrap up every program, I'm going to bring in all our classrooms to say a big thank you and farewell. So our Cochrane crew, Avoca West, Mr. Humiller's class, thank you guys so much. Have a wonderful day, everyone. Bye from the outside. Thank you, and see you soon.